you may want to hear me go over because most people did not get this one correct. And if you did get it correct, you guessed your way after I said no. Only a few people did get it right. All right, I'm pausing for corrections. For those who are correcting their work. Moving forward in about 30 seconds. If you need to take a picture, please do. If 30 seconds is not enough time. I'm also recording. I started recording at this point, so this should be showing on the screen. We're going to go over bell work 2 next. So you're very excited for this one. Is that organic stuff in it? Yeah, organic is like the elephant in the room. You kind of have to know it. That's why it was in the previous packet. You at least have to know pent means how many carbons?
5.
So if there's 5 carbons, how many hydrogens do you need to draw around those 5 carbons? It's 3 on the outside and 2 on the inside. So pentane would have how many hydrogens? 4, 5, 6, 7, 8, 9, 10, 11, 12. Pentane is C5H12. Butene is C4H8. Hydrogen molecules is H2. And hydrogen atoms is just H. So the question asks, which contains the largest number of hydrogen atoms? Number means amount, and moles are amounts. So if we figure out which one has the largest amount of moles of hydrogen, we'll figure out which one has the largest amount of hydrogen, because moles are amounts. We can say in moles. We don't have to use Avogadro's number. We can just change them all to moles of hydrogen. So the first one, 0.1 moles of pentane has how many hydrogens?
12.
Every pentane has 12. So how many moles of hydrogen would there be in total? What would you do? You would do 12 and multiply by 0.1. Does that make sense? If every one pentane has 12 hydrogens, there should be 12 times the amount of moles of hydrogen than the amount of moles of pentane. So this would give us 1.2 moles of hydrogen. That's the first one. The second one. I've got 0.2 moles of this molecule. Each molecule has 8 hydrogens. So, how many moles of hydrogen are there in 0.2 moles of butene? What would you do here?
6.
Correct. You would take 8 and multiply by 0.2. 8 times 0.2 is 1.6 moles of hydrogen. Third one. 1 mole of hydrogen molecules, and this is, you know, in a few lessons from now, you're going to be told to memorize the standard states. The standard state of hydrogen is H2, right? That's how it naturally exists. The 7 I've written on this periodic table that some of you may not be quite aware of, this is not a kid that went and just graffitied my periodic table. I did this. It's to tell us our diatomic elements. All the elements that are located in the 7 are the diatomic elements plus hydrogen. Those are all the ones that exist as 2. So hydrogen exists as 2. Well, 1 mole of hydrogen molecules has how many moles of hydrogen atoms then? 2, right? Because it would be 1 times 2. And then 6.02 times 10 to the 23rd hydrogen atoms, that's exactly 1 mole by definition of hydrogen atoms. So the most amount of hydrogen atoms is, does that make sense? Like my train of thought, the process? So whenever you're looking for something inside of a molecule, you multiply the moles out to get the amount. All right, so let's talk about what's going on. I've had to modify this week a little bit because unfortunately your class is getting the brunt of missed instructional time this week. At 1:45 p.m. today, half the class is leaving, so I have 1 hour to teach this lesson. So I actually took out half the lesson. I took out half the lesson. This should have other topics in there, so I'm going to put stars on the topics that I'm saving for Thursday that are not printed in here that I saved. I'm also then going to wait to give you your written homework until next class. But I did post some digital homework to do. It's already been pre-posted. And we'll talk about that in a little bit, but it's due, generally speaking, digital homework is due the night before the next class, just so you're aware. So some of them, if you are familiar with CK12, I know the students who took the class with me last year are familiar with CK12. Some of them are similar problem sets to what you did last year with stoichiometry, because it's not different than it was last year. It's the same thing. And there's one quizzes set for a topic that I did not find on CK12. It's called mass percent that you have to know. And so those digital assignments will be due before next class. And the next class will be ready to give out the Cambridge written homework. Also, we're plan to have your first lab next week on Monday, and plan to have a lab next week on Monday and on Friday. There should be 2 labs next week in this class. One's going to be on Monday, one's going to be on Friday. For the one on Monday, if you have hair that's shoulder length or longer, you're going to bring a hair tie. You will be working with the fire next week on Monday. I had initially wanted to do it this week on Thursday, but guess what? We're also going to be out of the class on Thursday this week because there's a fire drill and a lockdown drill under the new procedures during this class period on Thursday. And I was not about to have you all working with fire during a fire drill. So we're going to wait to do that lab until Monday. And also not working with the burners during a lockdown. We're not going to do that. We're not going to do that. So it messed with the schedule a little bit, but expect then plan to have a lab next week on Monday and on Friday of next week. This week then, we're going to start this lesson today, but some of these standards are going to have to be saved for Thursday because we're not going to have the full class time today. And for those of you that are hanging back, you can start working on the digital assignments when you're done. When we're done with the lesson, when everybody leaves, or half the class leaves to go do the 10th grade PSAT thing that you got to do. All right, so are we understanding what's up with the schedule? This week, pretty much lessons. Next week, you will still have a lesson on Monday, but the second half of the class will be a lab. So it'll be short lesson on Monday, and also the same thing for next week, Friday. The first part of class, you'll be learning about something that'll be incorporated in your lab in the second half of class. So let's go ahead and get started. Today we are going over stoichiometry. It rings fear in people's ears. We are here at stoichiometry. And we are not going to do molecular and empirical formulas today. We're going to do that on Thursday, unfortunately, due to PSAT administration. So I'm saving that topic for Thursday. But we will get through stoichiometry today. A brief reminder of what we spent if you took pre-ACE Chem or honors chem, what you should have spent weeks going over stoichiometry. So these are the standards. Some of these we've already done. We already did the unified atomic mass unit. We're going to do this on Thursday. We're going to do this on Thursday. We did this already last class, the anhydrous. And then perform calculations. This is today. This literally means we are only going over one standard today. We're only going over one part of one standard today. A. 2.4.1a. So that's, and then all of these other things we've either already done, and then these two we're going to do on Thursday, empirical and molecular formula. So the only thing we're doing today is we're going to use the mole concept to perform calculations reacting masses. What does that really mean? If I give you grams of a reactant, can you tell me how many grams of product are made? We have done this before. This is something that hopefully should just be a reminder of what to do. Okay, so what is stoichiometry? What is it? It is not a definition they need you to memorize, but it is a concept you should be well aware of. Stoichiometry is basically using a chemical equation to figure out amounts of reactants or products. So when we use a balanced chemical reaction to find amounts of reactants or products, this is called stoichiometry. There were 2 different types of stoichiometry you needed to be well versed in. One of them was called moles to moles, and the other one was called grams to grams. Moles to moles is the following. When you read a chemical equation, and we're not going to go over balancing equations today, we're likely going to do that on Thursday with the empirical and molecular formulas. But when you read a balanced chemical reaction. You're supposed to actually read it as moles. 1 mole of iron 3 oxide reacts with, so this means reacts with, 6 moles of sodium to make, this is called the yield sign, which also means reaction happens. 3 moles of sodium oxide and 2 moles of iron. Is the equation you're looking at balanced? Just a quick review. Is it a balanced equation? Why or why not? This equation that's written right here, is this balanced? What is a balanced equation? Go ahead.
It has the same number of atoms on each side.
Great. So a balanced equation has the same amount of atoms. Has the same amount of atoms of each element on each side of the reaction, right? So when you're reading this, is this balanced? How many irons are on the reactive side? 2. How many irons are on the product side? So how do we figure out the total amount of atoms on each side? You take the coefficient. This is what we call the coefficient. Same thing it means in math, the number in front. And we multiply by the amount in the subscript. So 1 mole of Fe2O3 has 2 moles of iron and how many moles of oxygen? 3 moles of oxygen. Yes? 1 formula unit of iron oxide, if I had just one of it, would have 2 irons and 3 oxygen atoms. And so you've got to be able to read equations correctly. Let me ask again, is this a balanced equation?
Yes.
Typically, if you see the numbers in front, it is likely already a balanced equation. If you don't see any coefficients in front, that likely means you have to balance it yourself. And that's a subject discussion for another day. Today we're going to be working with, I believe, already balanced equations to solve our questions. But if they're not, we will balance them in the process. So balanced equation has the same amount of atoms of each element on each side of the reaction. What does a balanced equation follow? What are we following when we follow a balanced equation? Are we following some kind of law? Yes.
Conservation.
Right. So this is the law of conservation of mass. Which means matter cannot be created or destroyed in a chemical reaction. It can only be transformed. You can move your atoms around in different ways and combine them in different ways, but you have the same total mass at the end of reaction that you had at the beginning of the reaction. You have the same amount of atoms at the end of the reaction that you have at the beginning of the reaction. So it just changes form. So we can, in this process, what you're doing is a type of reaction we're going to learn about. You may remember it's called a single replacement. You're replacing sodium and iron here. Sodium's replacing iron. All right, so how we read this? We read this in moles. Can you think of this conceptually? If I got 1 mole of iron 2 oxide, iron 3 oxide, and it requires 6 moles of sodium to react. If I had 2 moles of iron 3 oxide, how many moles of sodium would be needed to react?
12.
It goes up proportionally. So if I double the amount of any reactant, I double the amount of everything. And if I half the amount of my reactant, I half the amount of everything. So all of these relationships are proportional in nature, actually. And this is going to look crazy. This is what's called the mole map, meaning everything that you should have learned in pre-ACE of stoichiometry is here. Meaning you could go from grams to moles, and to go from grams to moles, you have to use the molar mass. Last class, we learned a quick little formula for that. Do you remember? It was moles equals grams over MR. So anytime I need to switch between mass and moles, I should be using that formula. That's what you all wanted to do. That's what you agreed on. What if you need to go from moles to particles? You need to use Avogadro's number. And you're going to have to decide whether you multiply by it or whether you divide by it. You multiply by it if you want particles, is the quick story, and you divide by it if you want moles. Volume. This is actually also something that was taught in pre-ACE chemistry or honors chemistry. You can go between moles and volume. This is going to be a lesson for another day. Because we're going to have a whole lesson on gases. But there is a moles to volume calculation in the moles. What we're doing today is this. We are going to be going from moles of some kind of given reactant or product to moles of a desired reactant or product. This is where we're at in the mole map today. And so this actually is it's kind of like a brainstorm of everything you could do with moles and grams and atoms. And so that's why I printed out to you. I printed out to you large just in case you wanted to use it as a study tool. Let's take a look at the types of questions we can have and see if you can figure them out. Stoichiometry review, moles to moles. Use the following balanced chemical equations. The first question is, how many moles of Na2O2 can be formed from 8 moles of Na? Do you remember what to do? My suggestion actually here is to use dimensional analysis. I do suggest using it, but if you hate dimensional analysis, there's an alternative. Dimensional analysis is to start with your given. And to place that under the number that you're given, you place the number 1. And then you multiply by a conversion factor. The bottom of your conversion factor is the unit you want to cancel. So you put the unit to cancel at the bottom. And you put the desired unit on the top. For moles to moles conversions, which is what we're doing right now, the conversion factor is the coefficient from the balanced equation. And I believe it said that in the big mole map, something like that. And so this is just a prep on how to do it. Really, all you're going to be doing is multiplying or dividing two numbers. It's just how do you set it up correctly. Look at the question for A. What you should do, just good strategy, you should circle what your given amount is and circle what you're looking for. That'll kind of tell you how many steps you have to take. We're starting with some really easy, simple examples. One step. You're given what? You're given, in the question, what are you given? What did they give you? They give you 8 moles of sodium. That's what you're given. You're being asked, when I have 8 moles of sodium, how many moles of Na2O2 can you make from that? Up here, your balanced equation, we like to call it our recipe, right? It's our recipe. I know that. If I've got 2 moles of sodium, I'll make how many moles of Na2O2?
1.
Right. So that actually tells you a ratio. It's 2 to 1 ratio. If you can think of that, and some of you may be able to think of this in your head, a 2 to 1 ratio, that means I'll always make half the amount of Na2O2. And if the numbers are easy, it's pretty simple. If I've got 8 moles of Na, how many moles of Na2O2 will I make according to this recipe?
4.
Right? Because if 2 moles of Na makes 1 mole, the chemical equation is basically your recipe. So the intuitive way to solve this, and are you allowed to solve this intuitively? You are. Cambridge allows you to solve intuitively. The intuitive way is to basically say, I have 2 of these, which makes 1 of those. That's the conversion. 8 of these will make, so 2 go to 1, 8 go to 4. And that will be the answer. That's the intuitive method. Now, what's the traditional method? Start with your given. Your given is 8. Put a 1 under that. This is traditional method. You have to pull the numbers from the balanced equation. And you get to have a choice. You have to put the correct unit on the bottom, the one you want to cancel. Because you start with sodium, you have to put sodium on the bottom, and you put Na2O2, which you're looking for, on the top. And so you would put 2 sodiums, or 2 moles of sodium, on the bottom. You would put 1 mole of Na2O2 on the top. You cancel out the moles. That's what unit conversion is. And then you do 8 divided by 2, which is 4. And the answers are the same. Yes? Kind of make sense? I'm going to tell you for sure the most often place you see stoichiometry in this course, the most often place you'll see most conversions is in the lab, believe it or not. Paper 3 is where this is going to show up the most. And you'll see next week on Friday, maybe even Monday. Definitely the second lab we do, and maybe even the first, we'll use some stoichiometry in there. So the most place you're going to see stoichiometry is in paper 3. There's a slight chance you see it in paper 2, and a decent chance you see it in a couple questions in paper 1, but paper 3 is the main place where this analysis will come into play. The lab is there, actually. All right, let's take a look at B. How many moles of O2 are necessary to make 5 moles of Na2O2? Can we figure that out? First of all, can you figure it out intuitively? Think about it. Na2O2, O2. The relationship. 1 Na2O2 is produced from how many oxygens? It is a 1-to-1 ratio. So the amounts will always be right? So the intuitive method tells us it's 5. I'm going to go ahead and write down the traditional method. The traditional method is to say my given is 5 moles of Na2O2. You start with your given, that's following this formula. Put it over 1. The unit I want to cancel now is Na2O2, so I put 1 Na2O2 because these numbers are coming from my recipe, which is my balanced equation. And what's the top number? What I'm looking for is oxygen. So I put a 1 on top for the moles of oxygen. I cancel out the moles of Na2O2, and my answer is 5 times 1 divided by 1, which is 5. Kind of okay with this? So the reasoning in stoichiometry is proportional reasoning. You have to understand how proportions work. And if I'm looking at a moles to moles question, I simply just look at the coefficients to figure out how many moles I'm making. But of course, it can't stay this easy, right? Let's take a look at the next question. So C. It asks, how many moles of Na2O2 are formed from 15 grams of Na? Oh, no. Have 15 grams of Na? But I can't use it. Like, the 2, the 1, and the 1 are not grams, are they? These amounts right here are all moles. All the coefficients are moles. So what do I do if I got grams? Oh, we're going to have to do an additional step, right? So if I've got grams of Na, and I want to switch it to moles of Na2O2, that means if we look at the map, we're actually right here. Do you agree? We'd have to go grams to moles, and then moles to moles, which means we're doing 2 steps. The first step, you can use your formula. use this formula to go from grams to moles. The second step would then be to use the balanced chemical equation coefficients. So let's take a look. Start with your 15 grams. We're going to do step 1. Once we've decided that we like this, moles equals grams over MR, right? I want the moles, I've got the grams, I've got the molar mass. The grams are 15 and the molar mass is? MR is the relative molecular mass, which we just called. For sodium, what's that? Easy numbers, 15 divided by 23, what does that give us? And how many significant figures?
0.65.
I'm gonna write 0.652. Just so you're aware, remember when you are doing multi-step questions, if you're gonna break them into separate steps, you should wait to round until the end. So I usually hold all the numbers in my calculator, but just to be careful, you should always write one additional significant figure. So that's why even though this is 2 significant figures, you're gonna see I'm writing 3. So it helps to eliminate rounding errors. That's the reason I'm doing that. All right, so that's my moles of sodium. What do I do now? Yeah, that's all. That's all I gotta do. So step 2 is to convert the Na moles to Na2O2, and you can either do this with the formula or you can do it intuitively. Either way is fine, but you've got to understand that it's 2 moles of Na for 1 mole of Na2O2. That's the recipe. And so I'm going to go ahead and write it the traditional way, which is 0.652 moles of Na. I write that over 1. I put what I'm trying to cancel at the bottom, which is Na, so I put 2 at the bottom. I'm writing it this way because it's how I teach it in freeze. It's how everyone in America teaches it pretty much. But you're dividing by 2. 0.652 divided by 2. So your final answer here should be 0.32 or 33, right? 0.33. All right, so if I see mixed moles and grams, what does it mean I gotta do? I gotta switch one unit to the other. So in this case, it meant change grams to moles and then do a moles to moles conversion. I don't know if you remember, you could either interpret this equation in terms of moles or you could interpret it in terms of grams. So if you have a gram to grams question, you could interpret the equation in terms of grams. I'm going to reteach how to do that shortly. Any questions here? We're okay with this process. Kind of familiar, a little bit familiar. One of the things that I drilled in creates over and over and over, like we spent a lot of time here. All right. In order to find the mass of the products, you'll need the mass of the reactant, the molar mass, which we call the MR, right? And the coefficients of the reactants and products. So, next question. This says check of 5. I always want to remind you, where am I pulling these questions from? This is from Cambridge Test. So, these questions, they're not past Cambridge exam questions. They are written by the same governing body, though, so they are good for practice. Oftentimes, these are easier questions than what you actually see on a Cambridge exam, but they're good to practice to get ideas down. That's why I use them. And there's wording here that's interesting. So they tell you, same equation, right? What type of reaction is this? Anybody remember? What type of reaction is this? Synthesis, or a combination, right? 2 elements, combining them together, synthesis. That's coming soon in a very, very short lesson. Very shortly, we're going back over the types of reactions. So that is something you're gonna have to know, like how to complete and balance reactions for sure. All right, so we've got it. So, is it balanced? did tell us, calculate. Calculate always means math. Whenever you see calculate in this class, it means do something with numbers. Whether you're multiplying, dividing, putting into a formula, you're doing some kind of math, right? So this calculate the maximum mass. I want you to underline that phrase because it is a source of confusion. That's why I like this question because it does show up on Cambridge exam. That phrase. Calculate the maximum mass of sodium peroxide formed when 4.60 grams of sodium is burnt in excess of oxygen. I also want to use the opportunity to tell you that Cambridge likes to use words instead of formulas. So what's sodium peroxide here? What must it be? It must be, even though you haven't learned what peroxide is, you weren't taught that polyatomic ion, I didn't teach it to you. You may know it on your own. This is sodium peroxide. And you can figure this out contextually two ways. One, because it's a compound, and it's the only compound there. That's one way to figure it out. Two, because they told you it was made. Formed means this is the product. So even though you may not have seen it, they can give you something you've never seen before. You can have to figure it then out by context. So we're looking for sodium peroxide. So calculate the maximum mass of sodium peroxide from 4.6 grams of sodium burnt in excess of oxygen. All right, next thing. What does excess of oxygen mean? Do you remember? Excess of oxygen. If oxygen's in excess, what does that mean we do with it mathematically? It means there's plenty of it. So we don't consider it in the math. It means there's extra oxygen. It is not the limiting factor. The limiting factor is the sodium. So when they tell you excess, it usually means just don't consider it. So I would say cross it out whenever you see excess, so you don't confuse yourself. You don't need the information for oxygen in this question. You're not being asked about oxygen. You're not being given an amount of oxygen, so it's not a limiting factor. So I've got 4.60 grams of sodium, and I want to calculate the maximum mass. Maximum mass has another name. It's called the theoretical yield. So point that out. Maximum mass is also known as, I'm going to write AKA, the theoretical yield. You may want to go back and have create notes and look at that lesson. What is the theoretical yield? Correct. So that follows law of conservation of mass. If I just blindly follow law of conservation of mass and I input this many grams of sodium, I'll get out X amount of grams of Na2O2. Not considering experimental errors that happen and that we actually lose some materials as we go along when we do labs. So theoretical yield is going to show up as a homework thing, so make sure you write it down because that's another word for maximum mass. And so all this is really asking for is calculate the grams. It's asking calculate the grams you could get of sodium peroxide. Maximum mass just means we can use law of conservation of mass to solve. So this is not any different from any question we've seen, except we have grams and we're looking for grams. Last year, if you took the class with me, I had showed you a way to do grams to grams calculations. I'm going to go ahead and show that now. So for grams to grams calculations, my suggestion was always instead of using moles here, to change the moles to grams. How can I change 2 moles of sodium to grams of sodium to get a grams ratio? How can I do that? If each mole of sodium is 23 grams and I've got 2 moles of it, can you figure out how many grams of sodium would be in your recipe on the reactant side? How many would it be? 2 times 23. Pay attention to what I'm doing. I'm taking the coefficient in the front and I'm multiplying by the atomic mass. And that tells me that instead of reading this as 2 moles of sodium, I can read this as 43 grams of sodium. So far following me? throughout. But remember, oxygen for this question, we don't need it, right? Yes. Oh, 46. You're absolutely correct. Thank you. 2 times 23, 46. And then for the product side, what would we do to figure out how many grams of product is made in this recipe? What could you do? Get the molar mass, and there's 1 mole of it. So just the molar mass, which would be 2 times 23 plus 2 times 16. 46 plus 32. 46 plus 30, 78. Check my math. Is that what you get? And that's the amount of grams. So instead of interpreting this equation in moles, we can interpret it in grams. And we can say that if I have 46 grams of sodium, I'm going to make 78 grams of sodium oxide. So now, using that, I have 4.6 grams of sodium. Can you figure out how much sodium peroxide that would make? What would you do? The numbers aren't so easy. They're not completely complicated. It's a ratio again, right? Go ahead.
So you find the moles of the 4.6, then you multiply that.
Right. So the idea is, when the math works out, and we can make it just one step by doing the following. We start by writing 4.6 grams of Na multiplied by. On the bottom, we put the mass of Na, so that's what you're saying, divide by 46, right? So we want to cancel that out, and on the top we put 78. And your answer should be 7.8. If you got 7.8, you got it. Yes? The alternative method would be to change grams of sodium to moles of sodium, moles of sodium to moles of sodium oxide, and then moles of sodium oxide to grams of sodium oxide, which is basically to do this. Like, you could do this, like go through the mole chart and do 3 steps. But I actually advise you, my suggestion is to just change the moles to grams when you're doing grams to grams ratios, and then just do 1 step, where you take the amount you have, and you make sure you divide by that mass, and then you multiply by the mass of what you're looking for. And that's what we call a grams to grams ratio, or a mass to mass ratio. We have another example. Let's see what far we're at so far. I told you we were only going to do stoichiometry today. So, believe it or not, we're not done, but we're only doing stoichiometry today. Check up 5B. So this is also from the textbook. Let's go through this process again, see if we kind of get the idea what to do. Tin 4 oxide is reduced to tin by, reduced. You know that word? The chemistry word, reduced. It's coming. Redox is coming. That's redox. Reduction oxidation. Coming later this unit. Tin 4 oxide is reduced to tin by carbon. Carbon monoxide is almost formed. That's terrifying. Okay. They give you in a reaction. Is this balanced? I left you space too. Underneath. It says calculate the mass of carbon that exactly reacts with 14 grams of tin 4 oxide. And then it says give your answer to 3 sig figs. So, I think, let's double check. Yeah. It's grams of carbon, right? And you have grams. So I advise a mass to mass strategy. So what did I say to do first for that? You should find carbon on here. And what else should you find? where's tin 4 oxide here?
First one.
The first one. So that's the first thing, is to identify what you're looking for and what you have. The next thing would be to change those moles to grams. In the recipe, you want to change the moles to grams for each one. So we're going to change this to grams. What would the grams of SNO2 be? Grams of SNO2. Tin is?
180.7.
And 2 oxygens?
30.7.
So 32 plus 118.7 is?
150.
So 150.7. And then 2 moles of carbon, what's the amount of grams of that?
24.
So 2 times 12, which is 24. So I know that my ratio is that it will require 24 grams of carbon to react with 150.7 grams of tin 4 oxide. Now what do I have? What's my given?
14 oxide.
So I've got 14 grams of SNO2, and the decision you have to make is what number do you multiply by and what number do you divide by. So what number goes on the bottom? So here's the deal. If you put 24 grams on the bottom, you're canceling carbon with SNO2. It has to be 150.7. Because whatever is on the top in one step has to be on the bottom in the next. And then this becomes 24 grams of carbon. That cancels. Multiply and divide, you get your answer. What's the answer here? If you've worked it out. I get 2.23. Does that make sense? Think about it like this. You should have a lot more tin 4 oxide than you have of carbon, right? A lot more. You had 14 grams of tin 4 oxide. So your answer should be a lot less than 14. Agree? And it is. Proportionally it is. All right, so that's stoichiometry. You're going to have to know stoichiometry moles to moles, and you're going to have to know stoichiometry grams to grams. And you also have to know, if you have a mixed moles grams question, how to switch the grams to moles. Now, there's one other part of this topic, and remember, this is just one part of one standard. The other part is something that went over, should have been went over in a first year chemistry class called percent yield. This will be most likely in your first lab on Monday, something that has to do with this. And hydrates is my other idea, and you'll be burning something. So you'll need the fire. But percent yield, what this is experimentally how much we got. Versus how much we should get. Yes. So what does that mean? When you actually run an experiment, you almost never get everything you're supposed to get. You don't get the amount of products you're supposed to get. Because when we do reactions, we're going to do our first experiment next week, there are some mistakes that we make, and there are some mistakes that are inherent in the equipment, actually. Sometimes your equipment is not very accurate, or it'll be every piece of equipment has some kind of error with it. And so because of that, there will be error in your measurements. Also, every time you move from one container to another, you pour a solution from one container to another, you leave some behind in the first container. So your actual yield is almost always lower than your theoretical yield. So the theoretical yield is, according to this, is what we're supposed to get. This is the theoretical yield. When we do this process and we use the balanced chemical equation, we go by actually doing the experiment. That's why it's called the actual yield, which is why you're going to start to see, that's why I said you're going to start to see labs now, because it's about to show up. And so the percent yield is basically just a ratio between the two. How much I was supposed to get divided by, or how much I actually got divided by how much I'm supposed to get, and then multiply by 100. So let's take a look. We have just a couple more practice questions before we're done for the day. It looks like. Practice question. A sample of zirconium is made by reacting 58.30 grams of zirconium tetrachloride with excess magnesium, according to the following balanced equation. So that you're given a balanced equation there. The mass of zirconium produced is 20.52 grams. Calculate the percent yield. And this is how a standard question like this looks. What you would have to figure out is, to get the percent yield, you can only figure out the actual yield experimentally, right? So that means you have to be told this. If you're not doing the experiment, and it's on a paper 2 or paper 1, you have to be told this. Or you have to be told that, right? You have to be told one of those two if you're not doing the experiment. So if you're looking for the percent yield, you have to be told the actual yield. What's the actual yield here? Yes. This is the actual yield. They just state it as a fact. This is the amount we got. The amount we got was 20.52. And it asks us to calculate the percentage yield. What don't they give you here?
The theoretical.
And it's almost always like that. You're almost never given the theoretical yield. So step 1 in a percent yield question is to figure out find the theoretical yield. And the theoretical yield is what Hakeem said earlier. It's the mass that could be, it's how much you could make of that product, yes. Go ahead, grab the pass. Step 1, find the theoretical yield. This is the mass that could be made. Do we have information to help us find the theoretical yield?
Yes.
Where is it?
The equation.
Well, we have the recipe, right? This is technically our recipe. And we've got this amount of 58.30 grams of ZrCl4, right? So, what should I do now? I've got grams of ZrCl4. I want to know, what do I want to know the theoretical yield of? Yeah. Zirconium. Because it says, calculate the percent yield of zirconium, right? So I actually want zirconium, so that's why I'm circling or putting a box around that. And I should have the information for ZrCl4. So I don't need the other pieces of information, I only need those two. It's mass to mass, so what should I do next?
Calculate the atomic mass.
Get the atomic masses. And is this balanced?
Yes.
Yes. So these are ones in front, so it's literally just get the molar mass of each. So I want the grams instead of the moles. Zirconium chloride. That's gross. What's the molar mass of zirconium chloride? Thankfully, they give you this. You don't have to look too long. By the way, if they give you this, this is a gift. We want to save you time that you don't have to look in the periodic table, so we're just giving you the masses. So you don't have to look it up. 233.2. And zirconium itself? Yes, that.
The values like
On the periodic table, they shouldn't be. They shouldn't be. Zr is 91.2, right? And so that is the ratio you have to work off of. 233.2 grams of zirconium chloride. Yeah, 91.2. And 91.2 grams of zirconium. Now where do I go from here to find the theoretical yield? I've got the mass of the zirconium chloride. I've got the mass of zirconium. What do I do now? Go ahead, Justin. Right. So I'm going to start with my 58.30 grams because this is my is my given. Put that over 1. And the way that it always works when I'm doing stoichiometry or any other dimensional analysis is that whatever's on the top here has to go on the bottom on the next step. That's what you got to remember. And it's always going to be the number you divide by. And so the number with zirconium chloride is 233.2. So that's what I divide by. And the number on the top is 91. Okay. All right, multiply the divide. Let's see what you get. 58.3 times 91.2 divided by 233.2. Just thought to myself, this is totally like a math class right now. Do you get 22.8? Is that my final answer?
No.
That's my theoretical yield. So now I gotta plug into the step 2. Find percent yield. Remember, the actual yield goes on the top. The actual yield here is, so put 20.52 on the top and put what on the bottom? 2.8 multiplied by 100. That person has very good yield. 90%. Right? Like 90%. That means they got 90% of what they were supposed to get. There's one more thing we need to go over before leaving for the day. We've got 10 more minutes, so before they call the 10th graders out. So we have one more topic to cover. And it's not that difficult of one, hopefully. This will probably be the easiest of the 3 assignments that I've posted. It's called mass percent. So mass percent means in any compound, you can actually find out how much percentage by mass of each element you have. And this is a relatively simple ratio you can get. So let's take a look at a simple compound. Let's take a look at carbon dioxide. To get the mass percent, the way that's easiest to do this is to first start by getting the molar mass. And the reason I taught teaching the molar mass by making a table is because it allows you to find mass percents really, really easily. So the mass of carbon dioxide, the MR, I would get that by taking 1 carbon and multiplying by its mass, which is 12. And then oxygen, I have 2 of them, and its mass is? And so the total mass of carbon dioxide is? All right, so here's what the mass percent is. If 44 grams is the total mass of the compound, can you figure out from this information how much percentage of the mass is just from carbon?
Yes.
And how would we do it?
44 times 0.12.
I would say close. The way to get the percentage of carbon is basically just to take the mass of the element in that compound, divide by the mass of the total compound, and multiply by 100. See if this makes sense to you. If I'm looking for the percentage of the mass of the compound that's carbon, it would be the mass of the carbon over the mass of the total, like everything I have, multiplied by 100. Does that make sense? The mass percent of carbon is the mass of the carbon over the mass of the whole thing times 100. So what's the mass percent of carbon here? I get 27.2%. So then what would the mass percent of oxygen be? Can you figure that out?
72.8.
Right. And there's a couple of different ways you could do it. You could do 32 over 44 times 100. Or knowing that there's just 2 elements there, you could do 100 minus 27.2. But you do have to know how percentages work. And so this would be 72.7% oxygen. And so that means I can analyze carbon dioxide, and I know that in carbon dioxide, 27.2% of all the mass is contributed from carbon, and 72.7% of all the mass is contributed by oxygen. This is something we call percentage composition. Composition means what is a compound made up of. We also call it mass per cent. That's the other way it's referred to. We're going to take a look at a couple of questions. I think this is going to end almost exactly on time for when those students are going to get dismissed. All right, 2 more questions. One from textbook, and then there's one Cambridge question at the bottom. We'll do the one from the textbook first. See if you can try this yourself. Calculate the percent by mass of carbon in ethanol. What would you do? Go ahead. Raise your hand if you have for carbon. What was your total molar? Not looking for the molar, the percent carbon. Okay. Yeah, do carbon. Let me see if you've got carbon. Let me see if you've got the idea for carbon. Is that oxygen? Yeah. That's right for oxygen. Yes, perfect. Anybody over here? What would you do? 9.52% divided by 100. All right, I'm going to show this process real quick. First thing I would do is get the MR of C2H5OH. The MR of C2H5OH is 46. So I would start by getting that. Now, how much is the mass of carbon in C2H5OH? 24, right? So you do 24 divided by 46 and multiply by 100. And so when you do that, I didn't write it down. I believe it was 2%. We have 52.2% for the first one. That's correct. Now what will we do for oxygen? What is the mass percent of oxygen in this compound? 16 divided by all the mass, which is 46, multiplied by 100.
It's 34.8.
34.8. And then hydrogen.
13.
6 divided by 46 times 100, which is 13%. Hydrogen. What should all these percentages add up to?
400.
Do they?
Yes.
Where can it round to and still be okay? Do you remember?
99.9.
Yes, that's right. So as long as it adds up to, should add up to 100%, and for sig figs it would be 99.9 to 100.1 is acceptable. Meaning you could round a little bit on either side. So if you rounded off by 0.1, it's okay in the final answer. If it all adds up to 99.9, it means that the rounding is okay. It's not that you did it wrong. So this does add up exactly to 100%. All right. Does this ring a bell? No? There will be an assignment. Don't worry. There's an assignment on quizzes for this. I will do the quizzes assignment. And I will be posting a quizzes assignment if I didn't already on this. This is the last question. Let's see if we have time for it. Last question. First thing, relative atomic mass we did last class. What's that again?
The average
Weighted average of
all the isotopes of the element.
weighted average. Of all atoms of an element compared to the unified atomic mass unit, which is 1/12 of carbon 12. You don't have to say 1/12 of carbon 12 anymore. If you do, that's fine. But they say compared to the unified atomic mass unit is the official explanation now. One for the weighted average of all atoms, and 1 mark for unified atomic mass unit. That's 2 points for the definition and then 2 points for the math. This is the first kind of complicated math question you're going to see. Let's see if you can reason it out. Well, actually, we can't do it. This will have to wait. This will wait, because I haven't taught empirical formulas yet. So I will wait on the rest of this till Thursday. You can try to figure it out on your own. But I will wait to solve it until Thursday. All right, so I know that for the 10th graders, you're going to be leaving soon. Not yet, I don't think, until they call the announcement. For 11th and 12th graders and 9th graders, this class does have all 4 grade levels in it, 9th, 10th, 11th, and 12th. So for 9th, 11th, and 12th graders, you're hanging back and you're going to be working on the assignments posted. There were 3 assignments posted in total. I would start with the quizzes, which is on Master